the Anisotropic Synchrony Convention in special and general relativity. The distant starlight problem is the most difficult problem faced by creation scientists. The problem is, how can we see distant starlight in a universe that is billions of light years across but only 6,000 years old? The simplest and most obvious solution would be to throw out the biblical date, as some Christians have. However, simply going with the simplest and obvious solution is just a form of giving up. It is a lazy way of simply avoiding the effort it might take to solve the problem. The fact that this type of compromise makes those Christians look good to the world has an added attraction to it. Over the years, many solutions have been offered, and they include light being created in transit, the speed of light slowing over time, and various forms of time dilation. Dr. Jason Lyle has proposed that the Bible uses what is called the Anisotropic Synchrony Convention that results from special relativity. In this video, we will look at the details of the Anisotropic Synchrony Convention and how it solves the distant starlight problem. These are the Lorentz transformation formulas. They form the cornerstone of special relativity, with the conversion term gamma at the bottom. The February 1st formula provide the transformations of space and time in two different frames of reference. You need to keep in mind that at everyday relative speeds, these transformations are imperceivable. When does an event occur in space-time? Surprisingly, this is not an easy question to answer because, based on relativity, there is no specific answer. Different observers will see different events as simultaneous. Furthermore, it turns out that there are conventions that you can choose that will change the events you see as simultaneous in distant points of space. If you have a spacecraft passed by the Earth with a relative speed of nearly the speed of light, from the perspective of someone on board the ship, two flashes occur at the same time. Someone on Earth will see these events differently. First, they will see the event at the rear of the spacecraft occur. Then, they will see the event at the front of the spacecraft occur. Those on the spacecraft literally have a different perspective now than those on the Earth do, as their coordinate systems are tilted with respect to each other. Let's take the case of a ship traveling really close to the speed of light relative to the Earth. One day, they both observe a star go supernova in a large Magellan cloud. According to the person on Earth, the supernova happened 148,000 years ago, but according to the person on board the ship, it happened only 21 years ago. Here are various events occurring in space-time at various distances from Earth as seen from Earth. Here is a comparison with those same events in space-time, as seen from a ship traveling at half the speed of light relative to the Earth. Here is a comparison with a chart of the same events in space-time from a spacecraft going at 0.9 c times speed of light relative to the Earth. What this means is that there is no absolute notion of what is happening now. Not only is an observer's perspective on what is happening right now dependent upon relative velocity, it also depends on the clock synchronicity convention that is being used. At the heart of this is the speed of light and the impossibility of measuring the one-way speed of light. The simplest way of measuring the speed of light is sending a pulse of light to a mirror and bouncing it back so that you have the time that it was sent and received based on the same clock. To measure the one-way speed of light, you need to send a pulse of light from one clock to another, with the two clocks being synchronized. The problem is that if these clocks are not synchronized perfectly, you will get erroneous figures. This is just a simple illustration of the problems that can arise when trying to measure the one-way speed of light. You might be saying at this point that you can measure the one-way speed of light as long as you and the clocks are in the same frame of reference and the clocks are synchronized. However, the key problem here is that the clocks must be synchronized at a distance. Now let's take the case of three observers at rest with respect to each other, but separated in space, each with a clock near them. Then the guy on the left sees them out of sync with the other two behind his, and the one on the right further behind his than the one in the center. The woman on the right sees the clocks as out of sync, seeing the other two clocks as behind hers with the one on the left being further behind hers than the one in the center. If the guy on the left sees all three clocks as synchronized, then the guy in the center will see both of the other clocks behind his with the one on the right behind the one on the left. The woman on the right will see all three clocks as out of sync with the other two clocks behind hers, and she will see the one on the far left as being further behind hers than the one in the center. If the woman on the right sees all three clocks as synchronized, then the guy in the center will see the other two clocks as behind his with the one on the left being a little ahead of the one on the right. And the guy on the far left sees both of the other two clocks behind his with the one on the right further behind the one in the center. Despite the fact that these three observers are at rest with respect to each other, they do not agree on whether or not the clocks are synchronized. Neither do they agree as to the order in which they are out of sync. The question is who is right about whether or not the clocks are synchronized. Quite simply, a clock synchrony convention is a convention for synchronizing clocks across the universe. The selection of a clock synchrony convention is totally arbitrary. No one convention is right or wrong. They are simply conventions. Each convention makes an assumption about the one-way speed of light within certain constraints. To fully explain clock synchrony conventions, it is necessary to introduce the term proper velocity, v sub 0. The proper velocity between any two objects would be the two-way or tangential velocity. Clock synchrony conventions concern themselves with radial velocity. If you have a spacecraft heading out from Earth, the time observed between departure and arrival will be the distance divided by the proper velocity plus the distance divided by the speed of light. The measured velocity will be x divided by t sub m. A little substitution in algebra gets us to here. Continuing the process produces these results. This results in the measured velocity being the proper velocity over 1 plus the proper velocity divided by the speed of light. This relationship holds for the case where all of the velocity is in the radial direction. The generalized form of this has the proper velocity over the speed of light multiplied by cosine theta, where theta equals 0 heading away from the observer. One of the results of this is that if theta is 1/2 pi radians, or 90 degrees, then that part of the formula becomes 0, and Vm equals V0. This is the result when the proper velocity equals the speed of light. Note that when the direction is away from the observer, c sub m is 1/2 the speed of light, and that it is infinity when coming towards the observer. Adjusting between clock synchrony conventions is pretty easy with the addition of this term to the main formulas, where epsilon is the adjustment factor between clock synchrony conventions. Epsilon equals 1/2 for the standard isotropic synchrony convention, 1 for the anisotropic synchrony convention, and 0 for the anti-isotropic synchrony convention. The entire range of epsilon, from 0 to 1, falls within the range of acceptable values within relativity. This is the formula for the radial measured velocity with regard to the radial proper velocity, generalized for any clock synchrony convention. This is the formula for measured velocity with respect to proper velocity, generalized for any angle and any clock synchrony convention. Here is the formula adjusting between the proper speed of light and the measured speed of light, generalized for all clock synchrony conventions. What all this boils down to is how you synchronize clocks. Is that how do you determine what is now? It is simply a convention under relativity. The math works for the entire range of possible conventions, so there is no one convention that can be said to be the truth. The observer is free to choose whichever convention he wants, and it can be for any reason, including that it is the simplest for his particular situation. However, among these arbitrary conventions, there are only two that have any practical or logical use. One is the Isotropic Synchrony Convention, in which the math is the simplest. The other is the Anti-Isotropic Synchrony Convention, which most naturally matches what we actually observe. The Isotropic Synchrony Convention, also called the Einstein Synchrony Convention, is the standard convention used for the clock synchronicity in physics, astronomy, and cosmology. The problem is that most people do not realize that it is only one arbitrary convention among many, as well as one of two of these conventions that has practical applications. The primary convention for the Isotropic Synchrony Convention is that the one-way speed of light is the same for the observer in all directions, specifically that the incoming speed of light is the same as the outgoing speed of light, which is equivalent to the proper speed of light. It needs to be remembered that despite the fact that this convention is commonly used, it is still just a convention, and that under relativity, the one-way speed of light cannot be measured independent of a clock synchrony convention. Furthermore, within a given clock synchrony convention, the one-way speed of light will always be measured as what is assumed by the convention, while the two-way speed of light will always be the proper speed of light, that is, c. In the Isotropic Synchrony Convention, clocks are synchronized across space and not time, such that any time you look at a distant object, you are looking into the past. This also means that what is considered to be happening now in distant parts of the universe are totally inaccessible. The Isotropic Synchrony Convention does result in unaltered Lorentz transformations. This is one reason why it is so commonly used. This also results in no alterations to the formulas of special relativity. This is the main reason the Isotropic Synchrony Convention is also referred to as the Einstein Synchrony Convention. The issue with the Isotropic Synchrony Convention comes from the formulas for what we actually observe from relative motion. Started with the generalized formula for the conversion between measured radial velocity and proper radial velocity, along with the formula for the relationship between measured velocity and proper velocity for any direction, and the formula between the measured speed of light and proper speed of light for any direction. The Isotropic Synchrony Convention ends up having an epsilon for these formulas of 1/2. This means that in the Isotropic Synchrony Convention, the measured radial velocity will always be equal to the proper velocity. This is, however, not what is observed. In fact, we've actually observed an object apparently traveling towards us at a speed faster than the speed of light. Its proper velocity would have been very close to the speed of light, but still sublight. The same thing goes for the generalized formula for the relationship between measured velocity and proper velocity for all directions. Within the Isotropic Synchrony Convention, the measured velocity is always the proper velocity. It also produces the same results for the relationship between the measured speed of light and the proper speed of light, where the measured speed of light always equals the proper speed of light regardless of direction. Despite the fact that the Isotropic Synchrony Convention is the one that is generally used in physics, astronomy, and cosmology, it needs to be remembered that it is just a convention. According to relativity, there is no absolute now in the universe. This not only means that different reference frames have different nows, but what you consider now, even within a given reference frame, still depends upon how you synchronize clocks. The Isotropic Synchrony Convention may be the most commonly used synchrony convention, but it is still just a convention. That fact needs to be kept in mind as you look at the Anisotropic Synchrony Convention. The Anisotropic Synchrony Convention is one of two clock synchrony conventions that has practical applications. The primary convention of the Anisotropic Synchrony Convention is that the one-way speed of light is infinite when light is coming towards the observer and 1/2 c when heading away from the observer. It needs to be remembered that despite the fact that both conventions are just conventions and that under relativity, the one-way speed of light cannot be measured independent of a clock synchrony convention. Furthermore, within a given clock synchrony convention, the one-way speed of light will always be measured as what is assumed by that convention, while the two-way speed of light will always be the proper speed of light, that is, c. In the Anisotropic Synchrony Convention, clocks are synchronized across both space and time, such that now in the Anisotropic Synchrony Convention is the past in the Isotropic Synchrony Convention. Another way of putting it is that in the Anisotropic Synchrony Convention, clocks are synchronized along the past light cone. The result is that in the anisotropic coordinate system, the past light cone is equivalent to the space axis. Here is the illustration showing the full range of epsilon equals 1 to epsilon equals 0, with the Isotropic Synchrony Convention having an epsilon of 1/2, and in the Anisotropic Synchrony Convention have an epsilon equal to 1. In the anisotropic version of the Lorentz transformation, the time formula has the addition of the term minus r over c to account for the difference in time between isotropic and anisotropic synchrony conventions over distance. Note that there is no difference in the spatial formula. This also relates to an additional time dilation factor related to the change in radius from the observer. Note that in any case where the net change in radius is 0, this extra time dilation factor is also 0. Also note the fact that this does not affect length contraction. In translating between the Anisotropic Synchrony Convention and the Isotropic Synchrony Convention, we have these two formulas. If you know the time in the Isotropic Synchrony Convention, to get the time in the Anisotropic Synchrony Convention, simply add R over C. If you know the time in the Anisotropic Synchrony Convention, to get the time in the Isotropic Synchrony Convention, simply subtract R over C. Here are two spacetime diagrams illustrating this difference. Both of these are from observers at rest with each other and in the same location. The first one uses the Isotropic Synchrony Convention, and the second one, the Anisotropic Synchrony Convention. Note that the further ones are shifted up the time axis of the graph. In the Anisotropic Synchrony Convention, now, when we bring in the formula for the relationship between the measured radial velocity and the proper velocity, and the relationship between the measured speed of light and the proper speed of light for all directions. When we insert epsilon equals 1, the relationship between the measured radial velocity and proper radial velocity proceeds as follows. It reduces to the exact relationship that is observed. The same thing goes for the relationship between the measured velocity and the proper velocity for all directions. Once again, it reduces to the relationship between measured velocity and proper velocity that is actually observed. In other conventions, such as the Isotropic Synchrony Convention, this is explained by a delay time in the speed of light. However, in the Anisotropic Synchrony Convention, it naturally matches what is observed. This pattern continues when you take the formula relating the measured speed of light in a given direction to the proper speed of light. When we substitute in epsilon equals 1, we get the relationship between the proper speed of light and the measured speed of light in any given direction that we saw earlier. It needs to be remembered that this and the other relationships were derived based on what would be observed in an isotropic synchrony convention, and yet it is in the anisotropic synchrony convention where these formulas actually represent reality. So we need to remember that according to relativity, there is no absolute now in the universe. This not only means that different reference frames have different nows, but what you consider now, even within a given frame of reference, still depends upon how you synchronize clocks. The Isotropic Synchrony Convention is a very practical convention in that events occur exactly when we see them occur and not at some time in the distant past. It is a very practical clock synchrony convention that has actually been used since ancient times. It is still used today in that astronomical events are time-stamped as to when they are observed and not at some time in the past. Here is a generalization of the Lorentz transformation formulas, as well as the other formulas for dealing with the various clock synchrony conventions. It is actually a pretty straightforward generalization of the formulas for the anisotropic synchrony convention. With these generalized formulas, you can check out all possible clock synchrony conventions for yourself. The key to these clock synchrony conventions is the adjustment factor, epsilon, which can have a value from 0 to 1. It covers the entire range from the surface of the past light cone to the surface of the future light cone. This yellow area not only represents the range that can be considered now, but also based on the shift resulting from different frames of reference. That means that there is nothing here outside the realm of standard relativity. The spatial component of the Lorentz transformation remains unaltered. The time component, however, is adjusted by adding the distance term along with the epsilon term, such that you end up subtracting from the standard Lorentz transformation r over c times 2 epsilon minus 1, meaning that this change reduces to minus r over c when epsilon equals 1, 0 when epsilon equals 1/2, resulting in the standard Lorentz transformation, and reduces to plus r over c when epsilon equals 0. The same thing happens for the time dilation formula where the extra term is minus delta r over c times 2 epsilon minus 1. Once again, in epsilon equals 1, the extra term reduces to minus delta r over c. At epsilon equals 1/2, it becomes 0, resulting in the standard time dilation formula. And at epsilon equals 0, it reduces to plus delta r over c. Finally, the formula for length contraction remains unchanged. The generalized formula for the relationship between radial measure velocity and radial proper velocity is as we've seen it before. The same is true for the relationship between the measured and proper velocity in any direction. We also have the same relationship between the measured speed of light and proper speed of light in any direction. Likewise, it is the generalized formula of the two formulas shown for translating between the Isotropic Synchrony Convention and the Isotropic Synchrony Convention. These generalized formulas work for the entire range of clock synchrony conventions. They are an important part of fully understanding the significance of these clock synchrony conventions. Feel free to have some fun playing around with them. It will help you understand this principle. Numerous ways have been proposed to synchronize clocks for measuring the one-way speed of light. However, they all have the same problem. They all assume a particular clock synchrony convention, even if the person proposing it does not realize it. The result is that when it is looked at in another clock synchrony convention, it produces the results expected from that convention. The most common proposal is to start with two clocks right next to each other so that they can be synchronized, and then move one of them out to a distance where it can be used to measure the one-way speed of light. The problem with this idea is that it involves moving one of the clocks, and according to special relativity, this very act would cause time dilation, throwing the clocks out of sync. The solution proposed is to move the clock so slowly that there will not be any significant time dilation. In the Anisotropic Synchrony Convention, if one of the observers would see the clocks as synchronized, then he measures the incoming speed of light as being infinite and the outgoing speed of light as 1/2 c. Another common suggestion is to send the signal to both clocks from a central source that would set the clocks at the same time when they receive the signal. The problem is that it assumes that the one-way speed of light is the same in both directions. This would not even work for an observer of two clocks in a different frame of reference. You would still see them as out of sync. You still have the same problem as you did before, that observers by each clock would see the other clock as out of sync. Furthermore, if one of the observers did see both clocks as synchronized, they would measure an incoming pulse as traveling at infinite speed with an outgoing pulse traveling at 1/2 c. This is exactly what would be expected from the Anisotropic Synchrony Convention. It has also been suggested to use a rod as a way of synchronizing two clocks at a distance. However, this fails to take into consideration the fact that no rod is perfectly rigid. Even a diamond rod would be sufficiently flexible to mess up a synchronization for measuring the one-way speed of light. Furthermore, we have the same problem that an observer at one clock would see the other clock as unsynchronized with theirs. And if one observer did see the other clock as synchronized with theirs, they would measure the incoming speed of light as infinite and the outgoing speed of light as 1/2 c. All attempts to measure the one-way speed of light suffer from one of three major flaws. The first is that they use a tangential direction, which will always produce the proper speed of light. The second is that they assume, without realizing it, the Isotropic Synchrony Convention. Finally, they are actually measuring the two-way speed of light. This one is quite clever in that it measures the delay time between two mirrors, with the signals being detected by the same device and the delay being measured by one clock. However, the path of the light between the two mirrors is tangential to the detector. As a result, all clock synchrony conventions will measure the proper speed of light. What is at issue is the radial speed of light. This is an experiment that has been claimed as showing that there is no difference in the speed of light in different directions. First of all, this experiment was not designed to test clock synchrony conventions. It was designed to experimentally test whether or not the Earth's motion affects the speed of light. Second, the comparison of the pulse arrival times at detectors 1 and 2 is not made by the detectors themselves, but by the computer, which the light pulses between the two wheels is moving tangential to. As a result, all clock synchrony conventions would measure the speed of these pulses as being the proper speed of light, which is what this experiment did. At this point, you may be asking, Wasn't the one-way speed of light measured with the moons of Jupiter by the Dutch astronomer Aurelius Roemer in 1676? Well, not really. That was the interpretation he made of his observations of the intervals between eclipse times. This not only predated relativity, but it assumed an isotropic clock synchrony convention. Now, he did succeed in measuring the proper speed of light, because even in the anisotropic synchrony convention, the time dilation effect due to distance is related to the proper speed of light. However, it does not qualify as a measurement of the one-way speed of light in the absence of a clock synchrony convention. The point, ultimately, is that you cannot measure the one-way speed of light without assuming a particular clock synchrony convention. Once you have done that, you always get results consistent with that clock synchrony convention. The main argument used against non-isotropic synchrony conventions comes from the isotropic synchrony convention being so ingrained that those making the argument cannot think outside the box. The thinking is that it cannot be real because, after all, the isotropic synchrony convention is what is used. However, non-isotropic synchrony conventions come as naturally out of relativity as does time dilation and length contraction. Another argument against non-isotropic synchrony conventions is why should light behave in a non-isotropic manner? While this is a legitimate question, it is ultimately a result of the way space-time works. Ultimately, the answer is that because of the way space-time works, you can arbitrarily choose a convention for synchronizing clocks as long as it falls within certain parameters and light behaves accordingly. The most natural objection to a non-isotropic synchrony convention is that it doesn't work that way. Light takes a definite amount of time to travel from one point to another. This misses the fact that, from the perspective of a photon, the trip is actually instantaneous because, moving at the speed of light, photons do not experience time. Ultimately, as with all motion, the motion of light is motion through space-time, and how we see that motion varies depending upon how we look at it. The key to understanding the fallacy of all objections to non-isotropic synchrony conventions is that they are insisting that only one is valid. Based on the assumption that only one can be valid, they will insist on adopting a non-isotropic synchrony convention under any circumstances is going against modern astronomy. Once you realize that all clock synchrony conventions are equally valid arbitrary conventions, the problem goes away. One of the arguments against the anisotropic synchrony convention is that it implies a progressive creation. While this might be true for the Einsteinian synchrony convention, it is not true for the anisotropic synchrony convention. Part of this claim is that more distant galaxies are older because of lower metallicity. However, there are problems with this claim that more distant galaxies are older because of lower metallicity. One is that there is another explanation for a pattern of reduced metallicity with distance that is based on the biblical description. If the universe started off as a homogeneous mixture of hydrogen, helium, and other elements as God was creating it, as the heavens are stretched out, gravity causes differentiation of these elements. So in a bounded universe, it is not surprising to find such a pattern of metallicity among galaxies. Another problem with the claim that more distant galaxies are older because of lower metallicity are actual patterns of metallicity among galaxies. I can find no evidence that more distant galaxies have lower metallicity. It might exist, but I turned up nothing. It should be a very easy thing to demonstrate, but the only chart I can find on the topic is as follows. And it shows no real pattern of decreasing metallicity with distance. Now, yes, the most distant one has one of the lowest metallicities, but that's not part of a pattern. This myth is 100% busted. This one comes from rational, wiki, and atheistic propaganda site that gets most of creation science wrong. I know this from first-hand experience of their treatment of a paper that I wrote and was published in AIG's Answers Journal. Surprisingly, in this case, they actually got the basics correct and recognized ASC as a perfectly acceptable, albeit obscure, sub-branch of special relativity. The setup of their argument places a mirror 5,000 light-years from Earth to reflect an image of the Earth back towards it. The argument is made that from a young Earth perspective, this mirror will not show anything to Earth for another 4,000 years. And that is true. However, it is not a problem, because unless you can get a mirror out there at a speed faster than light, this argument is just a thought experiment. Furthermore, it actually shows that there's a way that this approach could be tested, at least in principle. Once again, this comes from Rational Wiki. The claim is that this is just a change of coordinate systems and that it does not change reality. They then go on to indicate that being able to use a coordinate system where the Earth is fixed and stationary at the center of the universe does not mean that the Earth is actually at the center of the universe and stationary. The problem here, and probably deliberately, is that they're assuming that there is some absolute frame of reference despite the fact that relativity shows that there is none. They are right that changing coordinate systems does not change reality, but they're using a sleight of hand here. The sleight of hand being used here is that when you're changing between equally valid arbitrary coordinate systems, there is no actual reality to change. Under general relativity, neither geocentrism nor heliocentrism represents objective reality, but both are equally valid, being just a choice of frame of reference. The same thing goes with the Anisotropic Synchrony Convention versus Einsteinian Synchrony Convention. Neither one represents absolute reality. They are simply equally valid coordinate systems. Einsteinian Synchrony Convention equals Isotropic Synchrony Convention. In conclusion, choosing a clock synchrony convention is an arbitrary choice, and once this is realized, all issues with non-isotropic synchrony conventions go away. Yes, in most cases the isotropic synchrony convention is the simplest, but that doesn't make it the only valid convention to use. It turns out that this is not only true for clock synchrony conventions, but for things like geocentrism versus heliocentrism as well. As a result, if the Bible is using the anisotropic synchrony convention, there is no distant starlight problem. It is purely an artifact of using the Einsteinian synchrony convention. The fact that special and general relativity prevent us from measuring the one-way speed of light is the key to understanding this synchrony convention issue.